Hey folks, this is going to be a lecture on Taylor series, which is a topic that you covered in Calc 2. So technically this is a review, but it's probably a necessary review. So there's some pros here at the very beginning, some wordage. If you know enough about the derivatives of a function, you can figure out the function, but not necessarily by taking like antiderivative stuff. More specifically, if I know enough information about how the function is changing at a particular point, then I can actually figure out how the function is going to behave over here. And that actually is a pretty fascinating thing. So again, if I know enough information about the derivatives of a function, say at x equals 0 at the origin, say, or just x equals 0. If I know enough derivative information, then I can figure out what that function is doing at x equals 1 for many functions. Again, that should be an astonishing thing. So if I know where the function is at x equals 0, if I know the derivative, it kind of points me roughly, probably in the direction of where it's going to be at x equals 1, but it's still changing. But if I know enough about the second derivative, it'll tell you how the first derivative is changing, and then the third derivative tells you how the second derivative is changing, which influences the first derivative, which influences the function. It goes on and on. So we attribute all this guy to this guy named Taylor. In the form of Taylor series, where you say, I can tell you what the function is if I know enough information about the derivatives. We're going to use this notation f superscript parentheses n for the nth derivative. So we're used to f prime and f double prime, f triple prime, but after a while, stacking all these primes up there looks like a mess. So you put it in parentheses. And then the 0th derivative means don't take a derivative at all, it's just the function itself. So the Taylor series of a function says at x equals c is f of x is the infinite summation, it's a series of the nth derivative evaluated at c divided by n factorial times x minus c to the nth power. Okay, so let's do some examples. I mean, we've done this before, but we'll do some examples now. The classic place to start is with the function e to the x, and we're going to find the series at x equals 0. We're going to make a table at first to see if we can develop a pattern for these derivatives. And this one's relatively boring, which makes it a decent place to start. All the derivatives of e to the x is just e to the x. Evaluate them all at 0, you just get 1 over and over again. It's always 1. So filling out this formula, I have n factorial in the denominator. My numerator is just 1 over and over again because all the derivatives evaluated at 0 are 1. And then I have x minus 0 to the nth power, which simplifies to simply x to the n over n factorial, which is going to be 1 plus x squared over 2 plus x cubed over 6 plus, it keeps on going. And then by way, remind yourself that 0 factorial is defined to be 1. It kind of breaks the other definitions of factorial, but 0 factorial is 1, which makes this part here work out well. All right, so that's one of them. Let's try another one. Another classic one is the Taylor series for f of x is the natural log of x. And now we can't do this one at 0. The natural log is not defined at 0. So we're going to do it at x equals 1. We're going to shift it over by 1 and define it there, the Taylor series there. So again, we're making a table for here's my derivatives, or the nth, here's my n's. Now here's my nth derivatives. Natural log function has a derivative of 1 over x, which has a derivative of negative 1 over x squared, which has a derivative of negative or positive 2 over x cubed, which is a derivative of negative 6x to the 4th, so forth. And then we're evaluating all this at 1, so I'm plugging in 1 into all these things. The natural log of 1 is just 0, and that's going to account for my first term. My first term is 0, so I can actually just get rid of it. All right, so we're going to skip that term later on. And then evaluate the rest of these at 1 means I can just keep like the numerator effectively, and it's just 1, negative 1, 2, negative 6, 24. And then notice these are all the factorial numbers changing signs. And they're not necessarily the factorial numbers from over here, but they're shifted by 1. So 24 is 5 minus 1, or 4 factorial. 6 is 4 minus 1 factorial, but it's also negated. So if you think about it for a while, what we have is negative 1 to the n plus 1. That gives me the alternating sign times n minus 1 factorial. So I can plug that in here. I'm starting with 1 again because I got rid of the 0th term. The 0th term was 0, so I'm skipping that. Those red marks are aligned together. And so I have -1 to the n plus 1 times n minus 1 factorial divided by n. And then I didn't write it out here, but this is one of those cancellation things. This says start with n minus 1 and multiply all the way down. This one says start with n and then multiply by n minus 1 and all the way down. Well, the n minus 1 all the way down parts cancel out, and you're left with just n. So the summation from 1 to infinity of -1 to the n plus 1 alternating sign divided by n times x minus 1 to the nth power, which gives me x minus 1 minus x minus 1 squared over 2 plus x minus 1 cubed over 3 minus x minus 1 4 over 4, so forth. And then as a quick aside, what happens if I plug in 2? Natural log of 2 is then, according to this, plug in 2 here, I get 1s everywhere I have those parenthetical marks. Get 1 minus a half plus a third minus a fourth, keep going. And then the question is, does that look familiar? It should. We can talk about it in class if you want to ask about it. I want to give it away. I want you to think about it. All right, so where does that leave us? Well, it just leaves us with homework real quick. Find the Taylor series for sine of x and also the series for 1 over 1 minus x at x equals 0. They're both readily available to be found online. Actually, in your Calc 2 book, it's there too. You can check your work when you're done, but just go through the process of taking the derivatives, plugging in 0 in this case, and try to find a pattern and write out the Taylor series. Go through that process, and then next class period, we'll talk about why we care about this right now, and it's actually going to relate to differential equations. If you have any questions, send me an email, as always. Otherwise, that'll be the end of this video. All right, take care, everybody.